Now we're going to look at problem 2 in the curve sketching. Here's a problem with denominators, and to simplify it a little bit, I already showed the derivatives for you. So first we're going to talk about domain restrictions. That's going to happen when I have a denominator that could equal 0. So domain restrictions looks like if I factor this, x plus 2, x minus 2, I'm going to have two domain restrictions where x equals 2 and where x equals negative 2. Now what are those domain restrictions actually? Are they wholes? Are they asymptotes? Well, they don't factor out with the numerator, therefore they are both vertical asymptotes. So I have vertical asymptotes, x equals 2 and x equals negative 2. These are some things that we want to circle to highlight so that we remember to graph them. Next, we want to talk about horizontal asymptotes. Well, what do we have in terms of horizontal asymptotes? Looking at the degrees, I see the degrees are the same, therefore I use the leading coefficient. Therefore, the horizontal asymptote is y equals 2. Let's go ahead and highlight that. Now that we've done the domain restrictions and the asymptotes, perhaps it's easy to find some intercepts. Well, intercepts, remember the easiest ones is when we plug x being 0. That's the y-intercept. So the y-intercept is g of 0, which is, let's see, 0 minus 9. So negative 9 times 2 on the numerator, and in the bottom, the denominator, negative 4. So what's that going to make? We have 9 halves, so 4.5. So one of the points we know to plot is 0, 4.5. Is it easy to find the x-intercept? That's where the y is 0. I think in this case, yes, it is. That's doable. So the x-intercept where the y is 0, so that would be our function equals 0, and that's only where the numerator equals 0, and that gives us 3 and negative 3. So we have two x-intercepts, 3, 0 and negative 3, 0. Those are some more intercepts, some more points that we can circle that we can use. Now on to derivatives. Well, we already did g prime. See it above. Let's talk about where g prime equals 0. That's where the numerator equals 0, and that's where x equals 0, critical number. Also, where does g prime not exist? That's where the denominator equals 0. X squared minus 4 squared equals 0, and that's where x equals 2 and negative 2. But we already determined that these are restricted in the domain, so they are not going to be maxes or mins because they're asymptotes. But we can put them on our number line and should put them on our number line anyway. So vertical asymptote, critical number. Let's test g prime and see what's going on with g prime. So looking into g prime, something to the left of negative 2, such as negative 10, plugging it into g prime, and the denominator is always positive because of the squared, so the numerator determines the sign. So negative there, negative again, positive, positive again. So we know what our function will look like. Increasing, increasing, decreasing. Oh, silly. Let's repeat. Decreasing, decreasing. Increasing, increasing, excuse me. We know that there's a vertical asymptote happening here, vertical asymptote happening here, and therefore this guy is going to give us a relative down up, relative min. So I know that at 0 there's relative min, and earlier we plugged it in, we know that it's 4.5. So the intercept is the relative min. Let's circle that crucial point. Let's go ahead and look at second derivative. Second derivative up here. Where does our second derivative equal 0? That's where the numerator equals 0. And that looks like it's not going to occur anywhere. Positive. We can't ever get to this to be negative, so it's not going to make 0. And try to set it equal to 0, you're going to get imaginary values, so nothing. How about where g double prime doesn't exist? That's where our denominator cubed equals 0. That does happen at two places, but again, it's because the domain restrictions are there. We can still make our number line with those domain restrictions. Testing g double prime in our number line, picking something to the left like negative 10 and testing it in our second derivative. So testing it in our second derivative, it looks like we get negative, and then we get something between, which is 0. 0 plugged in looks like a positive ultimately. And then something bigger than 2 looks like a negative, plugging again into the second derivative, that function right there, the second derivative. So what does that tell us? Concave down, concave up, concave down. We know the shape. Vertical asymptote here, vertical asymptote here. Therefore, no POIs because vertical asymptote, no POIs, no points of inflections. So let's go ahead and put everything we know into our graph. Now, we've got 2 vertical asymptotes, -2 and 2, and a horizontal asymptote at 2. Looking at some points, I don't see nope, no negative y values. But I do have some sort of symmetry here. So I'm going to put the y-axis right in the middle and the x-axis just a little bit lower than the center. And let's start with the asymptotes, the first things that we found there, the asymptotes. So I'm going to find 2, and maybe we want to space this out a little bit. Well, I've got 4.5. We'll just count by ones this time. That'll probably be sufficient. So 2 and -2. Okay, and y equals 2, so here. Okay, so we have our asymptotes. Y-intercept is 0, 4.5. 1, 2, 3, 4.5. There's a y-intercept. X-intercepts are 3, 0, and -3, 0. And relative min is one of those intercepts. So this is a relative min. So I'm going to write that up here so it helps me guide my graph. Then I'm going to try to connect the points in a smooth curve. So I know before the asymptote, concave down. And I know the asymptotes are supposed to guide my curve. So I want it to be bending downward, concave down, and always decreasing before the vertical asymptote. So always decreasing. Then I know it's supposed to decrease and then increase to give me a relative min here. It's also supposed to be concave up. That makes sense. Let's connect those points, and there we go. Try to do your best at taking the time to approach the asymptote. Then we're going to see this last section is concave down, and voila.